Morning, morning, morning. Can you hear me? I was told with the lapel mic I need to speak like Martin Fowler very loudly. Is that all right? I think you can hear me. We're good in the front row. Like, step back. Not too far. Not too far. Morning. Thanks very much for coming. It's always a pleasure. I had a thing on Facebook pop up in one of those kind of like 6 years ago you were doing, and it was 6 years ago my wife like complaining that I was in Australia and she was having to put up all the Christmas decorations. And so I just reshared with, yeah, sorry. Same happened this time. So it's great to be back. I love YOW. It's probably my favorite conference all around the world. I get to go to a lot of them. So this talk is about a bunch of stuff that's been rattling around in my head. It's a continuation, actually, if you like, from the talk I was doing last year. I did a couple of keynotes here last year on complexity science and flow and team topologies and how complex adaptive systems and different types of networks lead to different scaling characteristics for your organizations. So it's a bit of a continuation of that. I've sort of dived a bit more deeply into this idea of flow. What is flow? What do we mean when we say flow of value? What is value? And the upshot of it all is that, it's kind of nicely encapsulated in this quote, really. If I turn this on, that would help, probably. Artificial intelligence is already here. We call them companies, and we get paid to execute the algorithms very slowly. Now, we used to do a thought experiment when we were talking about modeling RESTful systems, about going back to the 1950s. Imagine you're in the 1950s, or talking about messaging systems, and you're working for a company before kind of the advent of computers. And you think about things like, what would it look like? What would you have as an individual working in a sort of white-collar job, sitting at your desk? And you'd have forms that you would process. You'd have inboxes, you'd have outboxes, you'd have stuff that would come in one side, you would do some work, stuff that would come in, would go out the other side. Now, my hypothesis in this talk is nothing has changed, right? That's still exactly what we do. Most of the time, our day jobs is taking something with slightly less value, that's less valuable, and doing some activity to it and turning it into something that's more valuable, whether that's being a developer writing code, you're taking some form of spec, maybe a user story, you're writing some code and turning it into that code in a repository somewhere that can potentially be deployed, or whether it's a tester doing exploratory testing, trying to sort of understand whether that code is not correct, but is as defect-free as you can make it. That's taking something that's untested, less valuable, and turning it into something that's more tested. Essentially, we operate in a kind of factory-like manner a lot of the time, I'm afraid, people, and I'm going to talk a bit about that during the course of this next sort of 45 or so minutes. So this is the name of the talk, How Flow Works, but being me, there's a bunch of other stuff going on in my head, so I couldn't really limit it to flow and how flow works. So I sort of tacked on this thing on the end, and other curiosities, which is a kind of catch-all for a bunch of random stuff that I hope you might find interesting. Some of those things will be the surprisingly recent invention of all the things, why AWS and self-service ate your lunch. Are we engineers now? Phase transitions in oligarchic societies, bit of a shift at that one. Why traveling slower, counterintuitively, often makes you go faster. Why you should never sit next to the Cassandra admins, that's just generally good advice. And what Lego has taught us about batch sizes. Now, I've got two people in the room that I was hoping to troll. I've deliberately not used Gregor Hope's diagramming notation for queuing theory because I thought that would be funny to annoy him. And if you've not read Enterprise Integration Patterns, the author is just sitting here. And also, I'm going to murder probably, or at least completely misunderstand most of the work that Jez Humble did in continuous delivery and subsequent books. So apologies for that. You can go to those sources and hopefully you'll get set straight of all the nonsense I'm going to be talking over the next 45 minutes. Oh, and I'll be talking about flow, the flow of value as well. As the introduction said, I did a thing with Martin nearly 10 years ago now, so 10 years of microservices, scary. Also, I've been writing more recently on the patterns of legacy displacement with two of my colleagues, so go and take a look if you want. So life moves pretty fast once in a while. If you don't stop and look around, you might miss it. Now, I've been on the Thoughtworks advisory board, the group that produces the technology radar, for about 10, 12 years now, quite a while. And over that time, we've seen an amazing acceleration in technology. Like the tools we're using to manage like our work, the tools we're using to do things like automated deployments, all the version control tools, the orchestration tools for our runtimes, they're really recent. They're really recent in terms of when they sort of came into being, when they were invented or created. I mean, Android is like 2010, would you believe, right? I mean, that's not that long ago. So distributed version control first appeared on the Thoughtworks radar back in about 2010 as well, Git and Mercurial. Now, I mean, GitHub has completely changed, I think, the world. I think the world that we work in, anyway. But it's only that old. You know, before that, it was Subversion and CVS and things. AWS. We first started talking on the radar about AWS in 2011. Who'd have thought that would be a thing? This is a slide from the original training course that Thoughtworks did. We were the original training partners for AWS back in 2011. I was one of the first 4 trainers in the world for AWS. They assured us that they wouldn't want to ever do their own training. You know, there was no revenue there. Turns out they were telling porkies. And very soon after we started the training, they took the training over and ran it themselves. But still, AWS, blimey, why is AWS a thing? I like this little cartoon that speaks to it. One Monday morning, there's a CIO, and he says, I just heard about this thing called a platform, right? Apparently, we can do DevOps with it. I'd like one of those as a developer. Now we call them DevOps or platform engineers. Oh, sure, yeah, why not? I guess let's have a platform. This is why AWS is a thing. Now, I'm sure you're all familiar with queuing theory notation. Basically, infrastructure as a service platforms are MMC queues, where C tends to infinity. I've got people looking very blankly at me. Tough. You can look it up later. Then continuous delivery. I think continuous delivery was published back around 2012. We had that sort of appearing on the radar in around 2012. Which again changed pretty much everything. Microservices was around late 2012, I think, that first appeared on the radar, even though we didn't write it up until 2014. Yeah, microservices these days, everyone has microservices. I've got microservices, lots of them I just write them at home for fun. You can ask me, I'll sell you 12 for the price of 10. Microservices are everywhere, but the advice from me remains the same. You have to be this tall to use microservices. If you're not this tall, as in you're not doing automated testing, you don't have a automated path to production, probably you should not start with microservices. Start with something else, and then break things up later. If you are this tall, probably also still start somewhere else, unless you've got really specific requirements that means a distributed system is the right thing to build. So, Docker, 2014. Docker's only been around since 2014, pretty crazy. Kubernetes, again, around sort of 2015 that first appeared. This is now how life works. Everything we do is run by Kubernetes, if not all Docker now. Platform engineering teams first appeared in 2017. Platform engineering teams on our radar. So a little while ago, 6 years ago, we've been talking about platform engineering. Since then, it's platform product engineering teams or product platform engineering teams. Then it's product management for platform engineering teams, trying to hammer home the thing that they're products, right? You need to treat them like products. Do user research. Don't just build them and they'll come. Because if you do that, you end up with what my colleague calls, or former colleague, the half-assed or superficial private cloud. Which is, so this is when you put an API over your ops team, right? So you might say, you've got a service now, we've got service now, which our ops teams are using, and we'll stick a nice GUI over it so your dev teams can point and click and create a thing, and then that generates a load of tickets into service now. And then the DBAs and people go off and create the infrastructure. This is a thing that happens, it's definitely out there. You can tell this, because you'll see the following thing happen. Essentially, you'll ask, I don't know, I want a database cluster maybe. I need just say a UAT environment for my new product that I'm building, and you'll sort of submit a request for a UAT environment. And before you had your superficial private cloud, it would take 3 months, because the people would have to pick up the ticket, they'd have to go and provision the hardware, they'd have to go install it all, do all that kind of stuff, and then finally give it to you. After you have one of these superficial private clouds, you can ask for the same thing, and it will still take 3 months, because they've still got to go and provision the hardware, they've still got to do all this stuff. That's the half-assed or superficial private cloud. I just heard about this thing called a platform. Apparently it comes with a DevOps, and then 2 years on, okay, boss, we've implemented a DevOps, we have a platform too, but we still can't get anything done. Anyone resonate with that? No one. Everyone's awesome. So I wasn't going to leave you hanging there. I'm going to do a quick recap on queuing theory because I think it's interesting, actually, that in the context of flow, in the context of how work flows through different systems. So this is the system of I want to create some infrastructure, right? As a developer, I would like to get some new stuff so I can get some stuff done, whether that's testing or for a new product or whatever. So this is my representation of a queue. Sorry, Gregor. I'll keep going. And essentially in queuing theory, we have this idea of producers who are producing stuff and they push something into the queue, and then you have a number of service nodes that are processing those items on the queue. So this is any queue that we interact with on a day-to-day basis. This is Jira, this is our backlogs if we're developers, this is, again, ServiceNow, this is the queue at dinner when we go for lunch later, right? This is the same queuing that's happening when we go for lunch, and I'll come to that in a minute and why conference lunches tend to suck. Sorry. But this is essentially, this is the kind of notation for queuing theory. And then you have departures. And of course, the constant rate of arrivals in a queue, the rate of departures depends on how fast the service nodes process stuff and on the number of those service nodes. So if you think about RabbitMQ, right, if you have a queue, you can speed up processing of items on the queue by having competing consumers consuming things off the queue, or you can speed them up maybe by having one of those consumers be beefier and faster and able to process things more quickly. But that's pretty much the only options you've got unless you want a rate limit upstream. So that's kind of queuing theory. Now, when you apply sort of queuing theory, when you sort of think about different types of queuing theory, you have this notation MM1, where 1 refers to the number of service nodes. I've sort of pointed that out here. So an MM1 queue has a single service node, whereas an MMC queue has C service nodes, right? So you can scale the number of service nodes up to a particular amount, and that's C. And my assertion is that infrastructure as a service are MMC queues, where C tends to infinity, or at least C tends to the ability of your hypervisor to start stuff up for you. Now, a traditional ops team, you can think about a traditional ops team as a bunch of people as service nodes sitting behind a queue of requests to get stuff done, right? The flow of requests is coming into the queue. You've got a bunch of people in ops, and those people in ops are doing stuff as fast as they can. Now, the problem with this traditional method is that A, people take time to do stuff, and also people are expensive, right? They're scarce resources, they're expensive, these are highly skilled people. So you tend to be limited in your ability to get stuff done. The flow of work is limited by the number of people you can hire in your ops team, right? And their ability to process this stuff. So these are MMC queues where C, pointed that way, is the number of people in your team. When you've got your superficial private cloud, you've got a similar position, right? It's just you've put an API over the front of it, but you're still relying on your ops team to do most of the work. You're still having to hire skilled people to get stuff done. You've then got infrastructure as a service, which completely inverts this, right? Essentially, I say C tends to infinity in this case, the hardware that's provisioning stuff for you, your ability to take tickets off the top of the queue and provision stuff for your development team in a platform environment, essentially scales pretty much up to the ability of your hardware to process requests. So it flips the equation. You're no longer hiring lots of expensive people to get stuff done. You're now able to scale much more quickly, and that's why AWS is and other cloud providers are so successful. You've then got this new thing we've seen in the wild recently, which is the half-assed platform engineering team, where you've got infrastructure as a service servicing self-service requests really fast at one end, right, and the flow of value going really, really quickly, and then you dump a load of people who have to service Jira items off a backlog in front of it. I need to create the build pipelines. Oh, right, okay, well, let's do some work to create the build pipeline. Oh, no, we don't provide PostgreSQL yet. Oh, we need to build a thing that provides you Postgres on your platform. And suddenly you're constrained again by the ability to hire platform engineers, which also sucks. So I guess the point of this is thinking about self-service, because in all of these examples, essentially these are expensive and slow. But infrastructure as a service, because it's self-service, this is why AWS is the thing. It's fast, right? It allows us to get more stuff done more quickly. So just to drive that point home, I'm going to put a box around it and flash, woo, like that. Exciting. Anyway, back to our timeline. Platform engineering teams, then we had data mesh. I want to talk about that. It's data. And then we've got a bunch of tools around data, culminating in the meteoric rise of practical AI last year, and I'm sure we'll have lots more of this stuff. It'll be basically 90% chat, GPT, and LLM-related items on the radar this next time, with the rest of it JavaScript libraries. And I'm not sure if I prefer that, but I think I do, rather than the other way around. I should point out, this is the only AI stuff in this, apart from agent-based modeling later. But this is an example from Martin Fowler's site. There's a really good article from our head of tech in China about how you can use LLMs and prompt engineering to act as a sort of pair. So just take a look, it's quite fun. I promised talking about flow, so that's what I'm going to get onto now. And first, I'd like to sort of introduce a number of books that I think are kind of canonical when we think about flow, the flow of work, how work flows from soup to nuts, or as Daniel Terhorst-North says, from the lead time to thank you. Essentially, we want to think about the lead time to our customers saying thank you. So building systems, optimizing for flow. So first up, continuous delivery. This kind of completely changed the game back in 2012. I'm not going to talk too much about this because I think it's been kind of accepted that this is how we go about building software these days. This is how we safely and sustainably get software into production. If we're serious about engineering, if we're serious and disciplined about what we do, about our craft, and about our engineering. Then building microservices. I think building microservices is super fun. I'm out of order here. Hang on. There you go. Building microservices. This is super fun, not because it's about microservices. Sam Newman wrote that when he was working for us in Australia, but because it covers pretty much all the other things around building systems. There's testing in there. There's design. There's how to split big problems up into smaller problems, how to think about those big problems so you can decompose them. There's domain-driven design. There's deployment of these things. There's versioning. There's lots of really cool stuff in here, which is a kind of an overview, I think, of what we need to do as engineers in order to get stuff done, in order to improve flow. So that's building microservices. We've then got evolutionary architectures. Now, I've put this up because it's more recent, but I think it takes some of the still existing unsolved problems or hard problems around things like governance, right? The stuff that often impedes flow. I've got a quote later on about change request boards and architecture review boards impeding flow. And what evolutionary architecture, this building evolutionary architecture does, is introduce a set of techniques like fitness functions that we can include in our build pipelines to sort of help us guide the evolution of our architecture and actually sort of help think about these sort of decisions that often impede our progress or impede flow earlier on in our cycle. So shifting left, although I hate that term. We've then got a bunch of other sort of underlying sort of things, I think. The Principles of Product Development Flow. This is one of my favorite books. Don Reinertsen was here, I think, in 2015 or 17, one of the two. And he blew my mind. I mean, this book, I read it twice. The second time, I think I was old enough to understand it. It was, I don't know, it was probably only about 6 or 7 years ago I read it the second time. And it suddenly all sat with me after spending 25 years writing software. Suddenly I realized what the economics of what we do is about and why sort of lean software development, sort of single piece flow, why that is so interesting and important. So that's another one. We've then got Accelerate. So Accelerate, again, the first author, Dr. Nicole Forsgren, she's awesome. She's now at, I can't remember, Jez, remind me. Microsoft. At least he's paying attention. That's awesome. There was no delay there. But this is a super important book, summarizing the state of DevOps reports over a number of years. And it sort of looks to the properties of organizations that help improve our ability to get stuff done. It's important because it's peer-reviewed, and I think this is one of the only peer-reviewed pieces of research that we have in this space. And then finally, Team Topologies. This has become an automatic classic immediately on publication a couple of years ago. I like it for two reasons. The first reason is because my name is in it a lot, so I think that's good, for obvious reasons. And the second reason is because, and there's a lot of really cool stuff in there about cognitive load and how to think about breaking, about software, about the boundaries of our systems and how much our individual teams can take on and understand and that kind of thing. But I like it because it gives us a ubiquitous language That's the main reason I like it. It means we can all talk to each other using the same words and understand their meanings about something that's been very amorphous, which is the sort of organizational design for building software, so team topologies. And I like to think of this as sort of stuff we do that seems to work, and then sort of how it works. Right? We sort of this continuous delivery stuff. It seems to help us get stuff done. These blue-green deploys and canary releasing stuff seems to make sense. We seem to be able to get more stuff done. And then the economics and the sort of science, the peer-reviewed science, and the sort of ubiquitous language that we get from these other works. So, I did mention this thing about are we real engineers? This is another book for, I guess an extra book for you, Are We Real Engineers Now? But Modern Software Engineering by Dave Farley. He argued very strongly last year that given all this stuff that we have, given the fact that we now have repeatable ways of getting our software into production in a safe and sustainable manner, maybe we could start thinking of ourselves rather than as craftspeople than as actual engineers. It's been recorded, so I probably am going to sit on the fence. I actually think we are. I think we're getting there, but only if we do all this stuff. I mean, I work for Thoughtworks, and we have a set of sustainable defaults in Thoughtworks for our teams that we sort of expect our teams to be using, and it's all these things from these books, but it's also things like test-driven development. It's things like pair programming. When you have all this sort of engineering discipline and you do it all at once and turn it up to 11, I think we can pretty much call ourselves engineers. Moving on. So, I mentioned earlier, inboxes, outboxes. Work essentially flows in everything we do, whether it's physical stuff or whether it's just sort of informational stuff that we do, knowledge work that we do. Stuff flows as information for us through value streams, right? It's a bit different from orange, that moves through a physical supply chain, right? From like being picked off a tree into a supermarket, or it's a bit different for a car, which goes through a series of activities that turns raw materials through a gradually value increasing process into the car that the customer buys, which is the ultimate source of value and what you pay for. But for us, it's about information that starts off as an idea in someone's head and then goes through this series of stages where it accrues more value until eventually you can start maybe earning money off it, or it starts saving lives, or it does whatever. When I say through these stages, who's come across value stream maps before? I'm trying not to get you all to put your hands up too much. I know everyone gets a bit sort of fatigue of putting your hand up. So, again, no, joking. So this is a value stream map. Not everyone in the room has come across these. These are the secret weapons of many consultants, me included. This is the first thing in my toolbox. When I'm engaged by an organization, probably the first thing I'm going to do is start thinking about creating value stream maps for all sorts of things. Value stream maps for the value streams of the teams delivering software to the clients. Like, what do those value streams look like? Value stream maps for the path to production. Value stream maps for the software development lifecycle. Value stream maps are pretty easy to read. You've got on the top, you've got value-adding activities. So value creating time and those value-adding activities. And in this, you can see 3 days, 1.5, and half a day. This is from a real client. It's a simple one, but it's 3 days of software development on average, so 3 days of writing code, delivering a story, 1.5 days of testing, half a day of deployment. Right? So that's that kind of thing. We then have wait times on the bottom. So in this case, you had 2 days before a developer picked something up, on average. You then had 10 days after a developer had finished writing some code before the testers picked it up, on average. Right, so that could be from 1 to 20 days, if you think about it. And then 30 days after testing finished on average before it was deployed into production. So 30 days means that it's a 2-month release train, right? 2-month release cycle, more or less. So what this means is for an average, for the sort of normal piece of work, you've got an awful lot for the production lead time. You've got 42 days of wait time for 5 days of value-adding activity. 5 days people are actually doing stuff, taking the thing off their inbox and doing a thing and putting it into their outbox. The thing is, if you're that person doing the thing with a big, loads of stuff in your inbox, right, you don't realize all this wait time is happening because you're constantly busy, right? I'll pick up the next thing, move it on, pick up the next thing, move it on. It's only until we start to visualize the system, visualize our systems of work, that we get to see overall what the impact of things like 2-month release trains are. as I say, in this case, you've got stuff sitting around after being tested for 30 days on average before it starts making you money. That's inventory sitting there in the equivalent of a car, tons of cars sitting on a lot, waiting to be sold and basically degrading over time. This is a more complicated one from a real client. This is more, big organizations tend to have value stream maps that look a bit more like this. And on this, I've sort of annotated this value stream map with a number of different types of wait times that we normally see. Coordination, this is a classic type of thing we wait for as value flows through our systems. So this is when you're waiting on one or more other people to do stuff before you can get something done. So there's an example in this. This is great. These point out over here, is my laser working? Just about. So these are two different types of data teams. There's that data word again. Two different types of data teams. And they get a request in, and they've each got a canonical model that they're working on, right? I know two canonical models, they kind of didn't really get what the word canonical meant. And they just update each other's canonical model for a while. Whilst the developers, the developer team, this is developers here, and that's writing code. This is writing code there. They're just sitting twiddling their thumbs waiting for these people to finish updating their canonical models. So you're waiting on a number of different teams to get something done. You then have scheduling. So scheduling you can think of as waiting for meetings, waiting for release trains, waiting for architecture review boards, or waiting for change request boards. And in this case, there's a bunch of stuff here. There's a bunch of scheduling. There was some architects who created solution options in this organization, and those options had to go to a review board where the best option was chosen, and that would take between 2 and 4 weeks. So upstream, you're kind of waiting for, 2 to 4 weeks for something to happen. Fun fact, from Accelerate, and I believe I'm going to use the right words, I've used the right words, change request boards predict low performance. In the technical sense of predict, in the correct sense of predict. That means if you have change request boards or these sorts of blockers in your system, I like to think of it as like cholesterol in your corporate information arteries. Right? You're blocking this sort of information flow through your corporate arteries. But they predict low performance. If you have them, it predicts that you're going to be in the low performing groups as reported to the State of DevOps reports. And then finally, queues. And queues are everywhere. I mentioned queuing theory earlier. But you see queues everywhere where we work. So every single swim lane is a queue. Every single, kind of waiting for, there are queues of decisions that need to be made by the architecture review boards. Queues are everywhere. And sometimes we have all three of these at once. And this is another curiosity. It's why we should nuke shared test environments from orbit. Because often shared test environments, you see all three of these conditions happening. You're having to wait for different versions from different teams. So you've got this kind of annoying thing. You often have to schedule your work to be tested sometime in the future because there's a slot when the test environment is available and so on. So you get all three of these things happening at once. The interesting thing was if you start mapping out these sort of flows of work and start mapping out how long things take and how long teams are blocked by things like shared test environments, you can very easily start to justify spending more money on buying more of them, right? Because normally you have this, we can't have another one because they're too expensive. We can only afford one F5, or there's only one instance of that type of CRM thing we've got. But actually, if you've got like 10 teams blocked 90% of the time waiting on getting code tested, it becomes quite an easy economic case to make to actually buy a new one. Now, here's a sidebar on generative science. Generative science is this sort of newish type of science. Like normally we think of the scientific method as form a hypothesis about how the real world works, or maybe probably the null hypothesis, and then conduct an experiment, right, and see if the experiment agrees with our hypothesis. Dick Feynman used to say we should look at whether like our hypothesis agrees with nature. And if it doesn't, then our hypothesis is wrong. But generative science is slightly different. With generative science, what you do is you create a simulation, you create a model. And in that model, you try and simulate some aspects of the real world. You then run the model, and then you see if the model looks like the real world. And if it does, you can start playing with the model and ask the model questions and see if it translates into real world behavior. I got interested in this after listening to someone else who's been to YOW Dr. Anita Singupta, who I think talked about the Curiosity lander, so the rover that's on Mars. And she was talking about all the ways that all the things that NASA do before they get off the Earth with these things. They don't build redundancy in because redundancy is weight, right? So what they do instead is they do things like simulations and scale models and all this sort of stuff. These sorts of things. And here's an example of a really simple agent-based model. Now, did anyone use Logo in school or in university? Yeah, turtles, right? Awesome. Right, we've got some people who use Logo. Logo is a very simple programming language used to teach programming often, where you create these little turtles and you can move them around and go in circles and all sorts of cool stuff. NetLogo is a different type. It's an evolution. It's like a multi-turtle logo. Lots of turtles doing stuff, which means that you can sort of simulate agent-based models using NetLogo. And actually a lot of the sort of quite sophisticated science that's coming out of the Santa Fe Institute and other places is done using NetLogo, would you believe? I wouldn't if I were you, get too involved with it, because there's no modularity, and testing is an absolute nightmare. So when programs get too big, you just have to throw it away and do it in Python or something else, which is I can attest to. But it's super useful for small things. Now this is flocking behavior in birds, right? So when I say about you sort of model the real world, so in this you've got a very simple set of parameters. I think it's like turning circle, how fast they go, and how close they get to one another, these little turtles, or birds. And in this you can see there's kind of there's no flocking behavior, essentially. This is a set of agents that are just sort of behaving randomly. It's like Brownian motion. But if you slightly tweak the parameters, these systems undergo phase transitions often. Complex systems undergo phase transitions, and you start to see this really graceful, beautiful behavior that starts to look like the sort of thing we'd see in the wild. And this is what I mean by creating these simple models and then asking them questions. Another example would be viral spread. So if you've got a population, how fast do viruses spread in a population? And you can model this simply using NetLogo. This has got some very simple parameters around how close the agents get to one another, how infectious the thing is, and how quickly you recover and whether you're immune or not. And okay, this is a toy project, but clearly we've come through something that's been pretty awful, and maybe something like this might be useful. And it turns out this is how a lot of the modeling was done for COVID, right? For all the rules that we started to see being put in place were created using models like this. So Bharat Sim, this is from, so Thoughtworks built this in conjunction with a university in India. And this is EpiRust actually, which is a Rust-based framework to do, I can't say it easily, epidemiological research into the spread of COVID or other diseases. And this is Bharat Sim. So Bharat Sim is a deployed real-world version of this, which was used to model the spread of COVID in the Mumbai area. Now, there's tens of millions of people in the Mumbai area, so having a tool that allows you to do that is super interesting. And super useful, and this is where the 2-meter rule came from, or the 1-meter rule, or wear masks or don't wear masks, because you can impose these rules in the model and see what happens when you run the model and see if it gets better or worse, right? So super useful. Also, phase transitions in oligarchic societies, another curiosity. You can use agent-based models to show that trickle-down economics doesn't work, which is fun. So you can create these models which have, each agent starts with an amount of value, and then you run the model where they perform simple exchanges of value every single time. Every time you run the model without any controls, one agent ends up with everything, and all the other agents end up with nothing, right? So, that sounds familiar, right? And what this screenshot shows, when you put the market controls, or the equivalent of market controls for Western democracies, for capitalist democracies, into the models, the Gini coefficients for those countries pops out. So the Gini coefficient is the ratio between rich and poor, essentially. And so you can sort of show using these models that without market controls in place, everyone ends up with nothing and one person ends up with all the things. So interesting. Back to following the work, though. I sort of showed you these different types of wait times, common wait times, when we're talking about the flow of value, stuff that gets in the way of flow, right? Gets in the way of us getting stuff done. We've got synchronization, waiting on two or more teams before you can do stuff. We've got cadence or scheduling, waiting for a meeting to happen or something like that, and then queuing. So here's something from the principles of product development flow. The principle of congestion collapse. When loading becomes too high, we see a sudden and catastrophic drop in output. So I'm going to describe a scenario. I wonder if this will be familiar to anyone who's worked as a software developer on a software development team. So you're working pretty hard, right? You've got this massive backlog of stuff happening, right? Everyone's working flat out, but nothing seems to be getting done. Right? You don't seem to be able to deploy anything. You don't seem to be able to finish anything. You're constantly context switching. You're constantly having to kind of down tools of one thing and pick up another thing. And then maybe some hippo, some highly paid person says, "Oh, this is awful. Nothing's being deployed. Everyone needs to stop and do my thing because that's the most important." Oh, right, and things get worse. Right? This is an example of a system undergoing congestion collapse. When there's no slack in the system, when people are kind of context switching and so on, the whole system essentially grinds to a halt, even though everyone is working really, really hard. I should point that out. And you can simulate this kind of thing with really simple agent-based models. So this is a model of a highway, right? A highway. The agents, the turtles in this are just cars going along a highway. And when you run this model, what happens is, you see the behavior you see on highways during rush hour. There's no crash, there's no incident. It's just, if you see the red tail lights here, you put your brake on, person behind you puts your brake on, and you get this bunching behavior over time, right? And this is congestion collapse in this system. And it's purely caused by there being too many cars on the road, right? There's nothing you can do to stop this if there is above a certain number of cars. There is a phase transition above which you will always get this type of behavior. Of course, it's made worse, pointing out, if you're the people in the room that do that thing, which is, I'm just going to lane change to try and get around it. That makes it worse, definitely. And I haven't got time to show you that, but you can also simulate that. So don't do that, please, right? Stay in your lane in a good way, I think, not in the socials way. And you get this congestion collapse. It's the same thing that happens on our teams. Just purely the amount of work that happens can cause, the amount of work that we're doing can cause this congestion collapse, where you get to a state where stuff just isn't getting done anymore. It doesn't matter how hard we're working. Which brings us to the next principle from Don's book, the peak throughput principle. Control occupancy to sustain high throughput in systems prone to congestion. What we do as software developers on our teams, we work in systems that are prone to congestion, that are prone to this sort of behavior. So what can you do in order to limit the impact of congestion collapse? Well, we can do things like you borrow stuff from Lean, right? You use things like work in progress limits. Limit the amount of work that's in progress at any one particular point. Limit the amount of stuff that's in our queues. And this is what we do. You can sort of show in agent-based models as well. So this is another model. We've just reduced the number of agents, the number of cars on the highway. And just by reducing the number of cars, we avoid congestion collapse. Right? But again, this is just from queuing theory. The other thing you can do, and this is why smart motorways in the UK are a thing, is you can adjust the speed limit of the highway dynamically. So as you reduce the speed, the transition between the highway undergoing collapse and not changes. So if you can have the same number of people on the road but turn the speed down, you won't get that bunching behavior, which is why you have this sort of 40 limit thing going on or whatever. Next up, we've got the second queue size control principle. Don't control cycle time, control queue size. Or why going to lunch at conferences often sucks. That's what this bit is about. So imagine now we're going to go for lunch in a bit, about 12 o'clock, 10:30. We're going to walk out there, and there's going to be a row of buffet tables that you can go and get your lunch at, right? I don't know this is the case. I'm guessing this is the case. I'm not a conference organizer, so I can't tell you for sure, but it's 90% of the time it's the case. How long do you have to wait for lunch? Well, what happens is, at a certain point, the sessions finish, but before that, you've got a constant stream of people who are out there, the exhibitors, the people who didn't go to the last session, and they're the lucky ones because they can just go to lunch, they just get their food and walk through the system and start eating. But then the sessions finish. boom, and suddenly you've got this thundering herd of people who all want to go for lunch, right? That's what this is on the graph. Boom, you get this huge queue of people building up in front of the lunch tables. The problem is, of course, that the lunch tables can only service so many requests simultaneously, right? You've got this constant number of departures from the set of lunch tables, which is this constant red line of departures. These are hungry people arrivals, and these are satisfied people at the end. Now, the problem is how do you know whether you've got a problem if you're a conference organizer? He says, looking at the conference organizer in the front row, slightly sheepishly. I'm feeling a bit awkward now. How do you know, right? Now, typically what we say in our teams is, hey, we'll measure these things like velocity, we'll measure cycle time, we'll measure these kinds of things, right? But actually the problem with measuring cycle time is it's a trailing indicator of how badly you're doing, essentially. What you need to do instead is you measure queue depth. How many people are queuing in front of the thing in front of your system? You measure the number of tickets in your Jira backlog, or the number of user stories waiting for testing. Right? You can measure that, and that predicts the cycle time. But not only does it will predict the cycle time, but it's a leading indicator of cycle time as well. So if you measure queue depth up front, you get a much quicker idea of when things are going badly. This is what supermarkets do. They actually have cameras on the tills in supermarkets. So as they see the queues build up, that's when they get the ding dong, all staff to go on the tills or whatever, because they're monitoring queue depth and not asking people when they left how long it took them to leave. Same in airports when they open up more queues on the desks. So yeah, batch size queuing principle measure queue depth, not cycle time. Next up is batch size. This is the batch size queuing principle. Reducing batch size reduces cycle time. So again, you can see this by these graphs that I took liberally from Don Reinhardt and recreated. So if you look at, you've got two batches of work. What do I mean by batches of work? Well, say if you've got 100% of requirements that are going to go through your system, right? 100% of things that make up the product that you're building, right? And in this case, you're putting 50% of them into production, and then you're doing the next 50%, right? And you're going to take a certain amount of time to do that. So in this case, you're going to start earning money on this set of things about there. You're going to earn money on this set of things about there, right? And then the next set of things about there, right? But if you look at reducing the batch size, rather than have just two big batches, have lots of really small batches, instead of earning money, where's the laser gone? There, for this batch, you're earning money here. Right? You're earning money much more quickly than you are in this case for the same amount of work. Just reducing batch size is a thing. And we have things like continuous delivery to thank for helping us understand that. That's why continuous delivery is so effective. Breaking things up into small batches, pushing those small batches through your production line, through your build pipelines and into production is essentially the most economically viable way of doing, of improving the way we get stuff done. Batch size reduction helps us shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. Again, just to drive this home, the principles of product development flow, he talks about the effective queues. You get longer cycle time, increased risk, more variability, more overhead, lower quality, and so on. In fact, when I think about organizations these days and how teams work and how information flows through organizations, I think about this sort of tree structure. There's a bunch of people somewhere that are having these ideas. Maybe it's like the people who sort of order the portfolio of work. And then you've got this kind of tree of teams, of these sort of value streams that form this sort of tree structure ending in deployment into production. And in each of these points, you've got these queues. And actually minimizing the impact of these queues by doing things like value stream mapping, by visualizing the system in which we work, is probably the most effective way of going faster. So I promised, I think, in the abstract for this talk that I'll talk a little bit about modeling the domain of work, and that's what I've been doing. So I've been building a prototype, or a number of prototypes over the years, which you can use to understand how work flows through an organization. This is a little slice through that value stream map, the very complicated one. It's no use picking an easy one when you're trying to model something, right? You want to pick a hard one, see if you can model that. And this is the set of people who are creating like business cases, they're enterprise architects, they're trying to come up with solutions to all this kind of stuff, right? And we sort of model these as these little inbox, outbox, inbox, outbox, information, more valuable information, information, more valuable information. A set of agents, essentially, that can work together to get stuff done. And you can model the world of work using these simulations, these agent-based models. Sorry if you are a bit depressed by the fact that you can be modeled quite so simply as this agent, like picking stuff up, doing it and passing it on, picking stuff up, doing it and passing it on. Obviously, this is an approximation for me. It's not much of an approximation, it's pretty much all I do. I don't tend to think too much these days, fortunately. But this is kind of what we do. We pick stuff up, we do something to it, and we pass it on. In this case, we've got an enterprise architect who is, they deal with solution designs. They go to the enterprise architecture says no committee, probably not the real name. They kind of have to come up with business requirement documents. It's over here. And then they pick up this bit of work, or they go to the meeting, and then they turn it into solution options, or they turn it into meetings, or they turn it into saying no to people and that kind of thing. Right. And you can model these different types of agents. You can model humans, you can model computers, you can model virtual teams, actually, which is when we get together to coordinate. And then you can model the different types of synchronization, the different types of wait times as well in our teams. And you can turn all that into, as I say, into a simulation. What we did was quite fun. Is there any games developers in the room? No. It's Brisbane, they're all functional programmers up here, aren't you? So this is something called a behavior tree. Super interesting, actually. I don't know why I didn't come across these earlier in my career, but it's like a finite state machine, except in graph form. So essentially, you have a set of, at the top, you have an outcome, and then you have a set of behaviors that you can execute to get to that outcome. And then you can turn that into code, which is what me and my mates did in C#. And then you can run that code, and you can get simulations of different teams doing different things. So this is an example of that. We've got two teams. I'll just show you very quickly a simulation before I wrap up. We've got two teams, one working using single piece flow. So every time a piece of work is ready to be picked up, if I'm able to pick it up, I will work on it. I'll do some stuff to it. I'll write some code. I'll commit, and I'll move it on to testing or whatever it is. The other team is working in a sort of waterfall, 100% batch kind of way. So everything has to be analyzed before development can start. Everything has to be developed before testing can start, and so on, right? So classic waterfall software development life cycle. And when you run this, you see something quite fun. Obviously, this is the visualization of the agents scurrying about in the background. Nice 16-bit stuff going on. Agile team are deploying stuff. Waterfall team, not so much. And when you run these to completion, what you see every single time is you've got the red line, which represents the team doing single piece flow, and the blue lines representing the waterfall teams. And what you see every single time is very quickly the agile teams start to deliver value. Very quickly that value, it becomes cumulatively much, 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 much more than the waterfall team has delivered. And in fact, the lead times are orders of magnitude out, and the value is many orders of magnitude out if you're doing single piece flow versus waterfall. And this is just a really simple example of what you can do by thinking about modeling what we do in the world of work, and thinking about the domain model of what we do in the world of work. So I mentioned artificial intelligence is already here. We call them companies. We get paid to execute their algorithms very slowly. That tree structure is essentially the kind of algorithmic structure of the organization that we kind of work in. So how flow works, the curious domain model of how we work. So these are the sort of principles I talked about and showed you, almost like simulated a little bit. The principle of congestion collapse, peak throughput principle, second queue size control principle, and the batch size queuing principle. I want to drive this home. Batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization, without adding more people, or without having to go work harder, right, or work smarter or something. Just reducing batch sizes improves your throughput by orders of magnitude. I also sort of talked at the start of this about these books, which I think are like super important. These are the books that kind of have led us to the point where we can understand the economics and the practical way of going about writing software in a way that is repeatable and makes us kind of engineers. Right? This is kind of like stuff we do that seems to work, how it works. But then I think there's another set of things that underlie this stuff, right? So there's a bunch of information theory, there's a bunch of complexity science, and this is this is the sort of underlying thing that this stuff flows from. Finally, the last curious thing, I didn't mention the Cassandra admins. Come and ask me about the Cassandra admins afterwards. What would Lego do, right? That's the question, what would Lego do? So if you ever remember, like in the olden days, in the before times, Lego used to just come in a box, and it used to be all the stuff in the box, right? And you'd have to go through the manual and put it all together. What do Lego do now? Well, they split everything up into numbered bags, right? So you take a small number of, do that, next one, do that, next one, do that. So it turns out what Lego would do is use small batch sizes, and you should too. And that's all I got for you today, so thank you very much.